Yeah, Michael.
All right, guys, it's 10 o'clock. I'm glad to see all of you made it through the weather. It's again here. It's really wet outside. I think it's supposed to let up by this afternoon, so hopefully it'll be a little easier going home than it was to get here this morning. But I am glad that you're here. Thank you for making the effort to come on in. Couple of announcements here. I don't have a whole lot. There's a homework due tonight, but we're gonna mostly work on it today in class a little bit. So I have a feeling that's not gonna be too much of a problem. So we'll work on that, and then there will also be a homework that's due on Friday night. It'll be based on stuff that we're gonna be talking about obviously this week. So we haven't quite covered that stuff yet, but we'll talk more about that homework on Thursday if there are things that you'd like to discuss there. That's kind of about where we're at. I mentioned in my email over the weekend, there is a homework assignment listed in Canvas that I'm actually not going to have you do because we're going to just do it together. Basically, if you watched my video over this past weekend, you already saw half of those homework problems get worked, and I'm going to work the other half of them just for practice as well in class this week. So it shouldn't be a big deal as far as that goes, and try not to make it too heavy or too stressful for you as far as getting through this material. So that's all I have announcements wise. My main recap, well, this is this document. I'm going to start over here with this thing actually. This is the recap handout from sections 4.6, 4.8, and 4.9. So let me just get this up for everybody. This is the bottom half of that recap. If we take any matrix A whatsoever, remember last Thursday I talked about the null space, the row space, and the column space of that matrix. So one thing I definitely want you guys to be doing is learning this little chart pretty well if you could. The null space is a subspace of Rn. The row space is a subspace of Rn. And the column space is a subspace of Rm, right? And then there are dimensions here, right? The dimension of the null space is just called the nullity, just by definition. Yeah. And then the dimension of both the row space and the column space is just the number of pivots in the row echelon form, which is called the rank of that matrix. Okay, so those are the three subspaces that we would associate with this matrix. To find a basis for any of those three, you do the same thing. So the good news is you only have to do it once, and it's going to produce a lot of fruit for you, which is that you take your matrix, you reduce it into row echelon form. Okay, once you get it into row echelon form, then this little column here explains what you need to do next. In the case of the null space, you just have to solve the system by back substitution, right? The usual Gaussian elimination process. For the row space and the column space, you literally just take the pivoted rows of the row echelon form. That's your basis for your row space. Whereas the pivoted columns of A that correspond to the pivots in the row echelon form, those become the basis for the column space. So it's really pretty easy. Nothing too heavy here. Let's just remember the most simple formula to explain in the whole wide world here, this thing in the box at the bottom. Guys, if you take the rank of a matrix and you add it to the nullity of the matrix, all you're doing is you're adding the number of pivots to the number of non-pivots, and every column either has a pivot or it doesn't. So those two values have to add up to the total number of columns in your matrix, which is n. So easy enough, right? Rank plus nullity is equal to n. That's the rank nullity theorem for any matrix. That's going to be true. Okay. So anyway, this is having it all in one nice little compact table. And I kind of like to suggest that you try to learn it that way. That's probably the best way. Are there questions about that at all though so far? Okay, so we just kind of, and I know some of the homework that we're going to talk about is related to this. Actually, before we talk about the homework though, I want to talk about one other thing, and it's actually an entire section in itself in our book. So I'm going to take some notes here with you guys about this, but there's no homework in this section, and it's really just kind of a summary section. And what we're going to do in section 4.10, guys, is we're going to take the invertible matrix theorem, This is our invertible matrix theorem, and it's going to be revisited. We have looked at this before, of course, it should hopefully ring a bell, this invertible matrix theorem. So we've looked at this before, and I just want to add a few things to our list today. Okay, so let's just remember that we're going to let A be equal to an n by n matrix. Now, keep in mind, this recap here is for any m by n matrix. So here I'm specifically focused on square matrices where the m and the n are the same. But at any rate, the following are equivalent. The following are equivalent, and then there's this big long list of statements, right? And we have started this list previously. Let me write down a couple of the items that were already in this list. So the very first statement in the list is that A is invertible after all. Okay, so the matrix is invertible. And I'm just going to go dot, dot, dot. I don't want to rewrite all of the statements that we had before. I just want to focus on a couple of the ones that are maybe going to be more important for us. Can anybody remind me what the rank for an invertible matrix, what the rank would be?
N.
N, exactly. It's an N. It's a full rank matrix, so it would have a rank of N. Exactly. I'm just going to put more dot, dot, dots. We'll skip over some of the other ones. And I'm going to go down. The one that we left off with last was the determinant of A. What do you know about the determinant of A for an invertible matrix? Not zero. Good. Let's add that again, just to remind ourselves. So far, this is all very familiar news, but I'm now going to add H, I, J, K, L, M, N, and O to the list right here. Okay, so let's see if we can add a statement H. So this is where the new material is coming in. And statement H would like to tell us what is the nullity of this matrix. So if we have an invertible matrix, what do you think that the nullity would be? 0. Why do you think it's 0?
So that's good. It's N.
Okay, the rank is N, right? So look at your formula here, guys. If the rank is N and the total number of columns is N, then there's no room for any nullity at all. So the nullity would have to be 0. So for an invertible matrix, the equation is just N plus 0 equals N. Just works like that. Very, very easy. I don't know if I've ever explained what it means for something to be 0-dimensional. I mean, the nullity of the matrix is the dimension, it says it up here, right? The dimension of the null space is called the nullity. Guys, when something is 0-dimensional, it just means that there's no basis vectors. You can get away spending no dollars on this basis whatsoever. What it really means, in other words, is that if we actually looked at the space that is related to the nullity, which is the null space, that this subspace is literally just the 0 vector. Okay, so the null space is tiny. The null space is just the 0 vector. There's nothing else. So if you're trying to solve A times X equals 0, the only solution to A times X equals 0 will be 0. The vector X equals 0. That's the only vector in this null space. That's kind of what that means. So invertible matrices have a tiny null space. Okay. However, let's go on. Is everybody okay so far? Any questions? Hopefully making some sense. Let's talk about the columns of this matrix A. So the columns of A, what do I want to say about the columns of A? Well, if I take my matrix A, I already know that if I do EROs, I'm going to get pivots in every column. Will there be any free variables? Not if there's pivots in every column. If there's no free variables, then those vectors that you laid in that matrix, what did we say last week? It was a good thing about the vectors. If I lay a bunch of vectors into the columns of a matrix and I do EROs on it and I don't get any free variables, then those vectors were, say it again? Li. That's exactly right. They are Li. They are linearly independent. So the columns of this matrix would be linearly independent. That's exactly right. Okay, great. What else do I want to say about the columns? Well, I actually want to give you a formula for the, oops, should not say, this should say call space. The call space of A. Let's see if we can figure out what it would be. Now, the dimension of the column space is whatever the rank is. Well, that would be n, right? And the column space would be a subspace of, it says here Rm, but keep in mind that in my theorem right now, m is the same as n. Okay, guys, this is going to be very relevant for one of the homework problems we're going to do in a few minutes. I have a column space that is n dimensional, and it is a subspace of Rn. So it has to equal Rn. It has to be the full Rn. It cannot just be some smaller subspace inside of there, because if it was smaller than Rn, it would have had a lower dimension than n. Okay. Actually, what this really means, can I just say this in simple, in sort of slightly different terms? This just means that the span of my columns, right? If I look at what are they able to span, they can span the whole Rn. The entire Rn is spanned by the columns of your matrix. So look at what these last two statements have said. The columns of A are Li, and the columns of A span the full Rn. What does that mean? If I have a set of vectors that is a spanning set and they are Li, what are we going to call them? A basis. Exactly. That's the next statement. That's the next statement. Statement L, the columns of A are a basis for Rn. The columns of A are a basis for Rn, so they are linearly independent. They are a spanning set, which is really what item K says. So putting those two together, then the vectors that you're looking at are a basis. That's right. So far, so good? Now, it turns out the exact same three statements are true about the rows of the matrix in addition to the columns. So I'm going to add three more statements here, guys, which are going to be the same things for the rows. So statement M, the rows of A are Li. And then statement N is going to be that the row space of A is equal to Rn. And then statement O is going to be that the rows of A form a basis for Rn. Okay. So guys, good goes with good in this class and bad goes with bad. So if a matrix is invertible, we have all of these good things that are true. The columns and the rows are Li. The columns and the rows will span Rn. The null space will be trivial, right? All of these things are true together about A. Okay, so good goes with good and bad goes with bad, depending on whether A is invertible or not. You kind of think of it that way. Okay, so far so good? Let me see if I can mute this screen over here. Do interrupt me with questions if you have any. I want to try and do some of these theoretical homework problems now based on what's right here. It's super, super easy to do some of these once you have those things in place. So from tonight's homework, this is the homework you guys are doing for tonight. I want to look at section 4.8, 17 and 18 that are on that list over there. On that sideboard from section 4.8. Still raining? It looks like it might be. Okay, so 17 says, let A be an M by N matrix with the call space of A equal to the null space of A. And then they are asking us to prove that M equals N. Right, so that's gonna be the trick here. Probably shouldn't have muted this screen quite so quickly. So let's just remember, guys, the column space of A, right, it is a subspace of our M. That means that vectors that are in the column space have M slots each, right? Whereas the row space of A and the null space of A, I guess in this problem we're working with the null space. The null space is a subspace of Rn. So this is a super easy thing to answer. Something with M slots cannot be the same as something with N slots unless the M and the N were the same, right? It doesn't make sense. It doesn't make sense for something that has 3 slots to be equal to something that has 5 slots. They aren't even in the same universe. And so it just doesn't make sense. So let me write that down now. Just what would be my solution here. Really briefly, we won't write a whole lot here. It's just a quick one. The call space of A is a subspace of Rm, and the null space of A is a subspace of Rn. So M equals N. That's really all you have to say. If they live in different, if M and N were different, then you'd be saying the column space and null space live in different universes. So how could in the world could they be equal? They couldn't. They just couldn't. Okay, so that's really all you have to say there. Okay, that's number 17. The very next problem, if we're good with that, the very next problem is a similar one, although on number 18, A is going to be an N by N matrix. So it's actually a square size matrix. This time, this is with the row space of A equal to the null space of A. Now in this case, because the matrix has a square size, the row space, null space, and column space, they are all subspaces of Rn, right, in this case. And what we're going to do here is we're going to prove that A is not invertible. And I've kept my invertible matrix theorem on the board because I think it's going to help us. If A was invertible, so let's start it off that way. If A was invertible or A is invertible, then all of the things in this list are true about A. If A was invertible, all of these things would be true. And there's something in this list that talks about the null space. And there's also something in the list that talks about the row space. Let's see what it is. For an invertible matrix, here's what the null space is. And for an invertible matrix, here's what the row space is. Right? So they're saying here, assume that the row space of A equals the null space of A. Well, if you look at this, you can see that for an invertible matrix, that would not be true. The null space is tiny, just the zero vector alone, while the row space is enormous. The entire big Rn universe would be the row space. So you can't have an invertible matrix where the null space and the row space are the same, because they kind of go opposite directions. The null space becomes really small, the row space becomes really big. So let's just add that to our notes here. Then the row space of A equals Rn, and the null space of A equals 0. So for an invertible matrix, those are the facts that we know, and obviously, therefore, then these are not equal to each other. These are not equal to each other. One of them is the whole Rn, the other one is just 0. So I'll just say here, I'll just make the conclusion, right? So thus, A is not invertible. Because if A is invertible, we get this, conclusion that the row space and the null space would be different. That look all right? Yeah, so a couple little theoretical problems there, but once you have this on the board, you kind of see it all in one place at one time. I hope it becomes maybe a little easier to piece some of these things together. So far, so good? Okay, great. Somebody's got number 14 from 4.9 up here as well. Let's take a look at that as well while we're at it and while we have all this stuff up on the board to help ourselves with. So let's look at 4.9, number 14 as well. So I think I could pull this one up. This says assume that A is a 3x7 matrix with a nullity of 4. Oh, sorry. Yeah, the nullity is 4. That's right. And the question is show that the call space of A is equal to R3. Okay, so we just have to explain this basically. It says show it, just means kind of prove it, explain it. So, we have our M and our N values here, right? The 3 and the 7. So we already know, and I'm gonna try not to pull down the screen and put the handout back up again, but we already know that the call space of A is a subspace of Rm. In this case, that would be R3. So for the solution, let's just write that down. The call space of A is a subspace of R3. Let's be clear, though, that being a subspace of something doesn't make it equal to that thing. So I don't automatically get my conclusion yet. In fact, I haven't even mentioned the nullity yet, right, in my solution here. So I have a subspace of R3, but the question is, why is this thing equal to R3? Because there's tons of subspaces of R3, right? This piece of paper makes a plane, and that plane is a 2-dimensional subspace of R3, right? And if I make a line, as long as it goes to the origin, a line is going to be a subspace of R3 as well. So there's tons of subspaces of R3. So just because something is a subspace of R3 doesn't make it equal to R3. We have to kind of explain why it's equal to R3. So what else could we maybe work with here? Right, I would think the rank nullity theorem might be helpful. So we know what the nullity is. We know what N is. And so using that rank nullity theorem, we could solve for the rank actually, right? So let's actually do that now. Let's go ahead and reference the rank nullity theorem. So from the rank nullity theorem, right, the rank of A is equal to 7 minus the nullity of A. But we already have the nullity of A being 4. So this is just 7 minus 4, which is 3. Okay, so not only is the column space a subspace of R3, but the rank of the matrix is 3. Can somebody remind me what is, well, actually, I don't need a reminder. It's right over here. If we look at the dimension of the column space, this is probably hard for you to read, but the dimension of the column space is the rank. So this is telling me right here that the dimension of the column space is 3. Okay, so the call space of A is 3-dimensional. Because the rank tells us what the dimension is of that column space. Okay, guys, we're basically done. Because if I have something that's three-dimensional, but it's also a subspace of R3, then it has to be R3. You don't have subspaces of R3 that are smaller than R3, but somehow still three-dimensional, right? What are the smaller subspaces within R3? Well, they would be planes that are two-dimensional, or lines that are one-dimensional, or just the trivial zero vector space. Those are the only subspaces of R3. So as soon as you tell me that you're looking at something that's three-dimensional within R3, those two facts together make the column space equal to R3. So hence, we'll just add one last sentence here. The call space of A is equal to R3. Do you guys follow that okay? That makes sense? If it's three-dimensional and it's a subspace of R3, then it is R3. It can't be anything else. Just in case it's not totally clear, they do ask us a follow-up question, which I think is actually useful to look at as well, which is that they ask us, is the row space of A going to be equal to R3 as well? So there's a little second question here that goes along with it, which is probably good for us to think about for a second. Is the row space of A going to equal R3? Well, if we look at the dimension of the row space is also the rank. So it is true. So here, the dimension of the row space of A, it is equal to 3. That is true. That is true, and they're trying to bait you. They're trying to bait you into saying yes to this question, but the correct answer to this question is no. They're trying to bait you into saying yes because the dimension is right. It is three-dimensional. But the question is, why am I saying that it's not equal to R3? Well, guys, there's lots of things that are three-dimensional. Just because something's three-dimensional doesn't make it equal to R3. P2 of R is three-dimensional, right? We talked about this last week, but that doesn't mean it's equal to R3. The vectors are not the same kind of vectors at all. And if we think about this 3x7 matrix, let's see if I'm tall enough to. I'm going to try to just draw some dots here where these entries would be. Right, if I take the rows of this matrix, it becomes more obvious that it's not going to be equal to R3 because each row of my matrix has 7 slots. So what you're looking at is three-dimensional, but it is a three-dimensional subspace of R7, right? It's a subspace of Rn for the row space. Okay, so however, the row space of A is a subspace of R7. And something with 7 slots cannot be equal to a vector space with 3 slots, right? So if it's a subspace of R7, then hence the row space of A, even though it has the right dimension, it does have the right dimension of 3, but it does not equal R3 because it's not even living in that universe. It's living in a 7-slot universe, which is what R7 is. That make sense? The column space and the row space, they both have the same size. Their dimensions are both equal to the rank, but they can live in different universes, right? The row space lives in Rn, the column space lives in Rm, and that's 2 different universes potentially. All of this blue writing makes sense here, guys? We okay with some of that? All right, well, I've knocked off the 3 problems that are on the board over there. If you think of anything else during our break in a little while, we can add to that list a little bit. But I think those are the 3 I really wanted to do. They're all kind of semi-theoretical problems, but it's really good for like putting the invertible matrix theorem together with the recap over there. Like these problems really force you to think about these things. So I do like these problems actually. Okay, anything else about row space, null space, column space that anybody wants to ask me about? Is everybody getting the idea here? I would say between sort of memorizing this list here, right, making sure you learn these items here, and that recap on the side board over there, that's a huge summary of these last three sections or so of chapter 4. Yeah, so I hope that you'll spend some time to really try to get solid on all of that. Okay, well, every semester when I get to this point, I like to take a deep breath and I finally get to say, we're done with chapter 4. It's the longest chapter in the book, and it just feels like it takes a long time to get through this vector spaces material. So it's kind of a breath, take a breath and kind of relax for a minute after we get done with chapter 4. What we're going to do next is we're going to try to take further advantage of our past math experience. So when we took Math 250A, we were working with some of these vector spaces like R3, right? In fact, Math 250A is all about R3. So you guys spend a lot of time studying things that go on in R3 from a calculus perspective. And one of the big things you did in that class is you probably drew a lot of pictures. So there was like geometry, and you would have shapes that are these surfaces in 3 dimensions that you could draw, and you could touch and feel these things and have pictures of them. And the question comes up, well, it's kind of a bummer that in other vector spaces we can't draw those same pictures, right? But what mathematicians have tried to do is they've tried to add a geometric aspect to what a vector space is. So let's just remember, the guys, that a vector space is a purely algebraic structure. That is a purely algebraic framework. We have a bunch of vectors together with, what is it, addition and scalar multiplication. It's all algebra based. There's no pictures, there's no reference to any other branches of math, there's no calculus, right? But it's tempting, based on our experience with R3, it's tempting to try to add an extra sort of geometric aspect to this algebraic, very algebra-focused structure. And that's what an inner product space is all about. And I had you guys watch this video, so I'll just very quickly recap a little bit from it. Essentially, you're just taking your vector space, which has addition and scalar multiplication, and you're adding this extra gadget over here on the end, this extra little operator, which is the inner product operation, okay? It is completely motivated by the dot product that you used over and over and over again in Math 250A, right? So if you remember from 250A, the dot product was really helpful for finding angles between vectors and for finding lengths of vectors. And so we're going to try to do those kinds of things in a general vector space by adding this inner product idea. I'm sure you all remember that when you take 2 vectors and you dot them together, you get a number out of it. Okay, so no surprise there. The notation is a little misleading because it makes it look like there's slots here, but really not. Really, the inner product of x and y returns just a single number, okay? It's a single numerical value. And there's a bunch of axioms that I went over in my notes that you took on this video. 4 axioms to an inner product space here. If I take 2 vectors and a scalar, all of these would have to be true. So for example, the inner product of a vector with itself needs to be at least 0. Now, if you take the inner product of 2 different values, two different vectors, you can get negative numbers. This doesn't say that you always have to get a positive number. But if you put the same vector into the inner product twice, it has to be positive. And the only way it could have actually been 0 would have been if the vector itself was 0 that you chose in the first place. Okay, so that's an important axiom. When we're checking these axioms, I always recommend checking the number 1 first, because it's often the one that doesn't work out. And if something doesn't work out, you want to figure that out sooner rather than later. So putting it first in, I put it first in this list for a reason, and that is that this is the first one that I recommend usually that we try to check. Okay? So far so good out there? Yeah, and then the rest of these are just, doesn't matter which order the 2 vectors are taken in, the inner product of them is the same either way. If I have a constant that is stretching one of my vectors, I can pull that constant out of the inner product notation. And then the inner product notation is also good with addition. So if I have 2 vectors added together, I can split them up and do the inner product calculations separately, right? So all of these things are true for an inner product that's really valid. And where are these axioms? When I say something is an axiom, I'm basically saying that we are assuming it. We are taking it as a given. And why are we doing that? Well, it's because these are the same properties that the dot product has. So we're just adopting. We're adopting those properties of dot products, and we're saying, hey, let's assume those are the rules for any inner product. Right? So we're literally just stealing these rules from what we already know about dot products. So far, so good? That's just a really quick review of some of what's in the video. Let me write down a couple of other basic definitions here again, just to kind of get it summarized for you. I really appreciate you watching that video, by the way. It really helps us out. Here we can do so many more examples and practice, which I think is a good thing to do. So just as another very quick review point from the video, you already probably have this written down somewhere, but I just want to get the definition of the norm back up on the board one more time. This is the idea of taking the length of a vector. So we use these double absolute value bars to provide the notation for this. And the norm of a vector is literally just the square root of the inner product of that vector with itself. With itself. And because of the first axiom, I'm sure I mentioned this in my video, because of the first axiom, what's underneath the square root right there cannot be negative. So you're not taking the square root of a negative number. And so this will make good sense. This will be a reasonable thing. And then we also, right along with that, the other definition, these are geometry ideas, guys. These are geometric concepts that we are now adopting in any inner product space. The angle theta between 2 vectors can be calculated as the arc cosine of the inner product of x and y divided by the norm of x and the norm of y. So we take that fraction, inner product of x and y, and we divide it by the products of the individual norms of those vectors, and we define that to be the angle theta. Okay, and that again is motivated by Math 250A. You have some formula in Math 250A that the dot product of 2 vectors is simply the norm of one times the norm of the other times the cosine of the angle between them. So we're just taking that same equation and we're just imposing it now here on any inner product space as a definition. Yeah, that's all that's happening there. Then the last thing to just kind of review again from the video is that there are 2 primary examples of inner products. I've already been talking about the first one, which is if you have vectors in Rn. So if my vector space is Rn, in a very standard example of an inner product of two vectors, let's say A and B, it literally is, as you saw in my video, it is literally just the dot product of those vectors. So I'm just gonna write out what the formula is here one more time. A1, B1 plus A2, B2 plus dot, 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 dot plus AN, BN. Yeah, nothing surprising here. This is just your good old garden variety dot product from regular calculus. Yeah, nothing too crazy. And in the video, I actually checked all of these axioms. That's where it gets kind of tedious, right? So I made you suffer through on me going through this verification. We're not going to do it again right now, but you do technically have to check all of these axioms before you can really confirm that something is a valid inner product. The second most famous example of an inner product, the one that would be the most famous after the sort of dot product example, would be this one here, and I did this in the video as well. If we take continuous functions that are defined on an interval from A to B, this is another one of our vector spaces. We haven't spent as much time working with this one yet, but it's going to play a bigger role, especially when we go back to differential equations. So for right now, these are just calculus functions. You can just think of them as calculus functions. And if I have two functions, f and g, then in my video, I explained that one way to spit out a number out of those two vectors is actually to do an integral from a to b of f of x times g of x dx. So it would look something kind of like that. Right. And that also has to be verified. So in the video, I did that. I kind of suffered us through on checking the 4 axioms that they would be true for this as well. I know it's a little tedious sometimes to see that done, but I don't like to just throw things up here too much without verifying it a little bit. There are billions of other inner products, guys. These are just 2. These are the most famous 2. You will see in your engineering applications, in your engineering courses, this second one will come up a lot. It will come up a lot. So it's worth knowing it and hopefully being pretty familiar with it kind of going forward. Okay, what I am going to start on right now is, now that we got the recap done. By the way, are there any questions here first before I get excited? I jump ahead too fast. Does anybody want to check anything with me on this? We've got the motivation, which is the geometry. We've got the rules, the sort of the definition of what an inner product is. We've got the 2 most famous examples of an inner product, and we've got these geometry definitions of norms and angles. So we're well set up now to kind of dive in deeper on inner product spaces. But is there anything here that's making anybody a little uncomfortable we should maybe say a little bit more about, or are we feeling pretty good? Yeah, Jose?
So you said that in order for us to determine if it's an inner product space, we have to check all the axioms?
Right.
Okay.
Of course, if one of them fails right away, then you're done. And you can just say it's game over and you don't have to check the rest of them. We're actually going to be practicing that shortly here. Yeah, it's a good point. So speaking of that, what I think I'd like to do, I sort of promised you that if you watched my video, I'd get you out of doing a homework assignment. So we're going to do basically the 5.1 homework problems together. And some of them were already in the video and we don't need to do them, but I'm going to do some of the other ones. So if we can, I'll write them on the board. So I know you probably don't have them necessarily directly with you, but I'm going to do them not necessarily in order, but so maybe what we could call this in the notes here, let's just call this the 5.1 homework. It's actually in the Canvas, it's listed as homework number 12. So we're basically going to just do this one together and save you guys a bit of work on this. And I'm not going to do them in order though. I want to do them in a way that sort of pulls my lecture together in the most natural way. I don't want to be jumping all over the place. So I'm going to actually start with number 31, sort of towards the end of the assignment. And this one just says to come up with, I'm sorry, not 31. I meant to say 30. I meant to say 30, number 30. 30 and 31 go together. So let's start with 30. What 30 is asking us to do is to come up with a formula for the inner product of, let's say, u with the vector v plus w. Okay, and what you might notice here is that we have an axiom that involves addition. However, the axiom says that you can split up a plus sign as long as it's in the first slot of your notation. But what I'm giving you on this problem from the homework is that the plus sign is actually in the second slot. So if we wanted to simplify this, which is really what problem 30 is asking us to do, what could we do with this?
Use the second axiom.
Ah, yes, we could use the second axiom. Let me just label this as axiom 2 to switch the order of these. Did I do this in the video?
Yes.
Okay, I already did this in the video. Okay, great. So this is what I meant. I did some of the homework already in the video. So I'll do this pretty quickly because I think you've already seen this. But the idea is to just switch the order of the two slots and then split it apart by using axiom 4. So this would be the inner product of v with u plus the inner product of w with u. So you just switch the order like so. And then just to make it look like everything's back in the same order again, we could switch it back using axiom 2 again. And we could put the u and the v back in the right order and then add it to the inner product of u with w. So we have a formula like that. So we are allowed to split up plus signs if they're in the second slot as well of this inner product notation. The axiom tells us we can do it in the first slot, but then because we can switch the first and second slots, you can basically do it in the second slot as well. So this is all that that's saying. And then the related problem, which is the very next one, 31, all they do here is they just say, oh, well, in that case, why don't you come up with a formula for the inner product of u plus v with the vector w plus x. So they just give you this whole thing and they ask you to simplify it. They basically want this to be simplified. So, well, you can either start by just applying 30, or you can start by applying axiom 4. Maybe I'll start with axiom 4. If I have something plus something, inner product with another vector, I can split it up. So it would be the first thing times the second vector. So that would be the inner product of u with w plus x added to the inner product of v with w plus x, like so. So we just split it up. That's by axiom 4. Axiom 4 lets me split that up. That's splitting up the first slot. And now I also want to split up the second slot, basically breaking it all the way down. And to do that, I use problem 30. So by number 30, which is the next line I'm going to do, I'm going to split up the second slot, and it's just going to give you exactly what you would expect, which is 4 terms. The inner product of u with w plus the inner product of u with x plus the inner product of v with w plus the inner product of v with x. You just get 4 terms like that, and it basically just means you can kind of FOIL things out the way you normally would do for an algebraic expression. So nothing too surprising going on there. Okay. Take a look at that, guys. Make sure those two problems make sense. They kind of go together a little bit. Now, number 32, which is the next one I'm going to do, is very similar to problems that I often put on my exams. Hint, hint. Because this gives us a chance to really practice the axioms a little bit. So I'm going to go to the very next problem now, guys. We're just doing the homework together, right? Just making it easy here. So let's say that we have some inner product space with a vector v whose norm is 3. And we have another vector w whose norm is 4. And let's just say that the inner product of those two vectors is -2. So it's okay to get a negative value as long as it's not the same vector twice, right? So for two different vectors, you can certainly get something like that. So part A is asking us to compute the norm of V plus W, I think, yeah. V plus W here. By the way, the popular wrong answer is 7. People will just add these two, and it'd be nice if things were that easy, but it's not quite that simple. If I want to find the norm of this vector, I really need to use my norm definition here. So I have to go back to the square root of something. Let's just see if we can write it out. The square root of the inner product of V plus W with V plus W, right? It's going to look like that. And now, underneath this square root, I sort of have something that looks like what number 31 was, which is the inner product of something plus something with something plus something. And it comes out into 4 individual terms. All right, so if I FOIL out sort of underneath this square root, guys, if I just sort of FOIL it out, I would get, the inner product of V with V, and then I would get the inner product of V with W, and then I would get the inner product of W with V, and then I would get the inner product of W with W. It's going to look like that. Okay. So you get those 4 terms. Now, a couple of points here. This first term, the inner product of V with V, does anybody want to tell me what that would be equal to?
3.
Careful. It's actually not 3, I don't think. So this guy here, what is that? That's the inner product of the vector with itself. But the norm of a vector is the square root of that.
Square root.
So this should have been 9. Actually, let me write it as 3 squared, just so it's really extra clear. So guys, if you just kind of look at this formula, the norm of a vector squared would be the inner product of the vector with itself. So if I square both sides of this, it comes into this. Yeah. So here I'm not taking the square root of this yet. The square root is outside this whole big thing. I'm literally just focusing on the inner product of the vector with itself. Yeah, underneath the radical, it would be 3 squared. Right. Okay, and then to that we have to add the inner product of V and W. What's that equal to? -2. It's given to us right here, right? -2. Okay, the next one is the inner product of W with V. What would that be equal to? They did not give us the value for the inner product of W with V, but we have an axiom. The axiom says you can switch the order of the vectors in that inner product and it does not change the value. So that's also -2. And then finally, the norm of W squared is what this is going to be, right? The inner product of W with W would be actually 4 squared in this case. So if you work all of that out, the square root of, let's see, 9 minus 2 plus 16. Is that 21? The square root of 21 then? I did that right, hopefully. Yeah, so that's kind of how you do that. That make sense? You actually have to work at it a little bit. The answer doesn't just fall out instantly. Let's practice one more of those because I did say I like to put these on my tests. So I'll do a second one just to make sure that we've got this totally covered. The next one is actually part B, which is the inner product of 3V plus W with -2V plus 3W. So we're still using all the same values that we had before, but we're going to work it out with this expression this time. This time, we could get a negative answer. I don't know. We'll find out. That would not worry me because these are 2 different vectors, and we're just looking for a number here, guys. We're just calculating this number. By the way, is everybody realizing that I didn't even give you the inner product on this problem? I don't have a formula for you to use. The only information you have is just this right here. This plus all those axioms. That's all that we're using to solve this problem. We're not getting down in the trenches with specific formulas like these examples. We're not doing that here. We're literally just working surface level with the axioms to try to simplify some expression here. So why do I like to put these problems on my tests? Because it forces people to know the axioms. You have to know those axioms to be able to simplify these expressions. Yeah. Whereas if you're working with specific examples, well, we can calculate angles and norms all day long just using dot products or this integral or whatever. And you don't really have to know the axioms for that. But you have to know the axioms to do this problem. Right. So again, I'm going to take this expression and basically do a big FOIL of it. Okay, so I'm just going to FOIL it out. The inner product of 3v with negative 2v plus the inner product of 3v with 3w plus the inner product of w with negative 2v and then plus the inner product of w with 3w. Something like that, maybe. So I just FOILed out, basically FOILed out the expression that we had into 4 terms. Again, basically I'm using problem 31 to do that. Okay, with this first term, do you have a suggestion how we could simplify it? Pardon me? Okay, the third axiom talks about pulling out constants. So that's absolutely right. Notice that I have a constant c here. I can pull it out in front. You can also pull out constants from the second slot. I think, did I do that in the video as well? I hope so. No. Well, you can. If I asked you to simplify the inner product of x with cy, I bet you would switch the order, pull the c out, and then switch it back. Right, so you definitely have an axiom that allows you to do that. My point being that you can pull out both the 3 and the negative 2. And that will leave you with negative 6 times the inner product of v with itself. Maybe I'll just recopy that for a second. Won't simplify it quite yet. And then the second term, I can pull out both of these factors of 3, which actually makes 9, times the inner product of v with w. On the next term, I have a negative 2. I'm going to pull that one out as well. Times the inner product of w with v. And then on the last term, I have a factor of 3 that I can pull out, leaving me with the inner product of w with w. So this is just pulling out the constants. So maybe let me just add a couple little justifications here. The first step was by problem 31. This was by axiom 3. And now I just need to try to start plugging the numbers in, right? The inner product of v with itself would be what? Did it already over here, right? It's just the norm of v squared. So that would just be times 3 squared. And then plus 9 times, I think this was negative 2. And then the next one, we would have minus 2 times negative 2. Again, because the inner product of w with v is the same as the inner product of v with w. And then we have 3 times the inner product of w with itself, which would be 4 squared. 4 squared. Don't forget to square that. So it's 4 squared. Okay, great, guys. We've just about got it. This is negative 54 minus 18 plus 4 and plus 48. I think if I got my numbers right. And simplifying all of that, I think that comes out to negative 20. And sure enough, it is a negative number. And that doesn't bother me that because it certainly could be negative in general. So far, so good. Right.
Is there a reason you're not square rooting? I know you can't square root negative, but is there a reason?
Oh, the square roots only come in when you're doing norms. So if I asked you to find the norm of a particular vector, we would have a big square root over it like we did on the first part.
So what are they asking you to do in part B then?
Just simply calculate this thing. And because it's not a norm calculation, you're literally just going straight into the boiling it out and simplifying term by term. Yeah, there's actually no square root that shows up in this one at all. Yeah, look okay? If you need more practice, guys, on your own, you can try part C, but I don't think I assigned it, so I won't do it. But that's number 32. Let's do one more and then we'll take a little break. I want to do 36, I think it is, back over here. And then after the break, we're gonna do a few more of the homework problems as well, and then try to go into the next section a bit. Okay, so on this one, 36. It's actually a proof. As well, so again, kind of semi theoretical. Let me just do part B of 36. There's an A and a B, but I think I'm just gonna do part B, which says prove that if you take the square of the norm of V plus W and you add that to the square of the norm of V minus W, that you get 2 times the norm of V squared plus the norm of W squared. So it's just a proof. It's actually not that hard. Let me draw you a picture though. This is, after all, a geometry chapter, so it'd be nice if we actually had a picture around. Let's say I have a vector V here and then I have another vector here, which is W. So then V plus W is actually this vector right here, yeah? Probably they show you this in physics or something. So you just add the vectors sort of head to tail like that. That's V plus W. If I draw the vector W just parallel down here and I draw the vector V just parallel over here, you actually make a nice little parallelogram out of the 2 vectors. And so the V minus W is actually this vector going the opposite way. So this is actually V minus W. And so the left side of the equation is just adding up the squares of the diagonals. So this is a theorem about parallelograms. And you can prove it using vectors, essentially is what this is. So the square of the sums of the squares of the diagonals of your parallelogram adds up to the sums of the squares of the 4 outside parts, because you have 2 of the V's and 2 of the W's and you're adding up their squares. Isn't that kind of cool? So if you know what these sides are, 3 and 7 and 3 and 7, right? You can basically take 3 squared plus 7 squared plus 3 squared plus 7 squared, and you know that will equal the sums of the squares of the 2 diagonals across the middle of the parallelogram. That's not obvious, I don't think. A lot of people don't know that fact, but we can actually prove it in the context of this inner product space stuff that we're looking at. So let me just, is everybody impressed by that? Yay, yes, we actually have a picture to go with something here. Yes, anyway, the proof of this is actually not hard. All I have to do is sort of write out the left-hand side and simplify it, and I'm just going to see that it's the right-hand side. It looks a little intimidating at first, but it's actually not so bad. Maybe I'll come back. Give myself just a little more space, though, to actually write it all out. Okay, so let's do that. Let me come over here. Let's just do it right on this board right here. So if I take the left side, guys, let's see. I bet you guys could do this. You don't really need me to do it, but I'm just trying to save you a little bit of time. Let's just start on that left side and see what happens. So when I square a norm, when I square the norm of something, it's literally just taking the inner product of that vector with itself. So in this case, it's going to look like the inner product of v plus w with itself. And then added to that, the inner product of v minus w with itself. So we end up with that. Okay, and now once again, I'm going to use that problem 31, which says I can totally FOIL this out. So I'm going to get the inner product of v with w, sorry, v with v, plus the inner product of v with w, plus the inner product of w with v, plus the inner product of w with w. All of that is just the first term. And I have to add that to the FOILed out version of the second term, which is going to be the inner product of v with v minus the inner product of v with w minus the inner product of w with v, and then plus this double negative, so it becomes a plus the inner product of w with w again. So those are 4 terms added to 4 more terms if I take it all the way out. And what do you notice that I can do? Canceling, right? I've got the inner product of v with w canceling with its negative, and the inner product of w with v canceling with its negative. And we look at what we have left, and what I have left is 2 of the inner product of v with v, and I have 2 terms of the inner product of w with w. And I think everybody sees where this is going probably. We're trying to get the right-hand side. So you see there's a factor of 2. We're going to factor all the way out. Right? We take that factor of 2 out, and I'm just going to skip a step here. The inner product of v with itself, I can just replace that back in with the norm of v squared. And the inner product of w with itself, I can replace that back in with the norm of w squared. And that's the whole thing. So it's funny how something that looks so computational and kind of dry as a calculation actually explains a very much alive picture of something that a geometry person would be interested in. Okay. I have done already half of the homework. I have a few more problems from this assignment that I'm going to do, but let's take a break first. I think we've been going for a while. Let's take 10 minutes, let you guys stretch your legs, find out if it's still raining. I bet it is. Great. Just open those up. No, that guy's walking pretty slow. I don't think it must not be raining too hard. Means taking a little break.
Your YouTube monetized? How much?
That maybe someday when I, can fully devote effort to it, I would do that. I have a pretty good, there's a lot of people like following my channel.
You have like 4,000 subscribers.
Yeah, but everybody watches for 2 minutes and then turns it off. Like, I got my answer, I'm done.
Dang.
Yeah, there's a couple of my videos that, most of them just have like my own students watching them, but then there were a couple of them that I noticed like 60,000 people have watched
Wow.
one of my videos. I was like, whoa, how did they find that?
Struggling students.
Kind of crazy.
on your physics?
Where did you get this one? I put zero, but I put zero too. I don't know. I don't know what you. Yeah. Okay. I put zero. I hope that's right. Because the Gaussian surface wasn't larger outside the surface. Yeah. I was like, that's way too easy. I don't know. I thought like if you deal with like so much information.
Was it easy?
I thought I was. I didn't get the box one. I know I messed that one up.
Like flux through a box or something?
No. I got it for the second question. Electric flux one. I got like 2 times 10 to the negative 5 and then negative 2 times 10 to the negative 5.
Or for $8 Tender Tuesdays, man.
So getting like stops.
Yeah. So
I think about it. I don't know. I know it's meant something, but I don't know. I just got like that and then the negative of that. You always learn the opposite direction. Yeah. So maybe I did better than I thought. I also got A for everything. Oh, you did? You got A. No, the answer was A. I think the answer was A.
all A, all answers were A.
Well, there's only 3.
We had 3 questions.
Yeah, it's 3 months. 6 questions.
That's fair. So tenders.
We're good. Let me know.
Wait,
Get that.
bruh. 4 tenders normally is $9.
That's A.
Bruh. That's so
What is big is that?
dude, I have to make tenders. They were having chicken size. Yes, because Amy was here, but good luck. There
Was it here?
Was it the one? I like it.
Because I got on the other day and they gave me extra 1 or 2 because they were tiny.
But like,
What's wrong with you guys?
normally I always finish that. I got like halfway through. They were just huge. Yeah. It's awesome. Yeah, I'm confused. Was it like a Bulgari?
That's what I'm doing.
I don't even remember. No.
Buns. It's your buns.
I don't remember what the code was. I clicked on it. Can't believe that.
Yeah.
Did you just get notification?
No, I don't have my notifications on for links. Why? It's really fast. Be fast. Are you serious?
I didn't see it. I didn't see my notification.
It's right now.
Yeah, this is
I need to upgrade my cards. I can't. Like advance because my cards are like it's not even like my game and it's holding me back right now. It's just my card.
You're just ass.
You say that. And I'll beat you.
Can't see
I'll make lots of
Play the better one. That makes leaked. I love these photos. It's it made it on my spam. I like your I like your color. Your sticker. Oh yeah. Did you like my sticker? Yeah, something. That's where I am. That's where I'm. Read Karuko. How long was she home? Oh, she's back already, right? She left. This is my favorite midnight last week.
Yeah.
Oh, you like that? Hilarious. I thought that was really good. It was funny. The son of Mossy Post. Damn, Reed. This is your one account? You only have the signal.
Alex is like. Tons of goodies. Of stuff that I know we have like this, yeah, it's a region.
This is all your pens. A lot of them. That wasn't. That was like half. That was like 5. You look. You. That was like a year ago. Which was really. Well, actually, we kind of finished the homework in class.
Wait, so you don't want us to turn it? assignment?
Tonight's you do. need to
Tonight's,
turn in,
yeah.
But number 12, I actually made it so you can't turn it
You
in.
can't make, yeah, okay.
Yeah, so you won't have to, do it. We're doing it right now. But there will be 13 will be coming for you to do, so that'll be what I recommend you. So, yeah. But that depends on me covering some of it. So, I have some time, I should be able to get to it today. It's always a tricky section, getting this part done.
Yeah.
I have to go pretty fast through chapter 5. Faster than I would like, but at least it's not as abstract. Most of this is more formulas and plug and chug.
And we'll finish 6 on Tuesday for our exam.
Just 6.1, yeah.
Just
6.1. I would like, in an ideal world, to start 6.1 on Thursday. We'll see if I get that far. So I still have to cover quite a bit of stuff in chapter 5.
Okay.
So, but it's not that difficult overall.
4 was the
It's
longest.
easy for me to say. Yeah, chapter 4 was by far the longest chapter. Most of the other chapters, we only need like 2 or 3 class days on it to cover. Yeah. For sure, for sure. All right, well, guys, I think most folks have made their way back over here. Hopefully you're enjoying the plug and chug nature of this. Oh, we have math problems where we actually get a number for an answer again. That's like what happened to that in chapter 4. Yeah, so this is a little more computationally driven, which hopefully you're going to enjoy that a little bit. It's not quite as conceptually challenging. I've made a note here. I'm just going through this homework assignment that you're not going to be turning in, that you can't turn in because I took away the submit button on this assignment. But this is just all from section 5.1, and we did several of the more axiom-driven problems before we took the break. And I wanted to just note that a couple of the other problems from that assignment were actually my examples in the video that you already watched, so I won't do those again. But I did dig one more up that is actually not on the video that might be good to practice. This is another type of question that I do tend to put on my exams because it forces us to think about the axioms of an inner product again. So let's take the vector space. This is number 10 from 5.1. Let's take the vector space of the 2x2 matrices and let's make this formula. So nobody can stop us from just making a formula. We can do that, of course, if we want to. But the question is, will it be valid? will it be a valid formula? Now, these double subscripts that you're seeing here, those just line up with the notation of a matrix, right? So if I have A, it's gonna have entries A11, A12, A21, and A22. And B is, of course, the same thing, B11, B12, B21, and B22. It's gonna be this kind of notation. And the question is, would this be a valid inner product? So I have to verify if these axioms are true. These are the 4 rules for an inner product. And as I mentioned, when I was reviewing this, I always like to start with the first one. Okay, so I'm gonna just check the first axiom here and just see how it goes. Axiom 1 would be, the inner product of A with A. The same vector twice in both positions. And if I translate that into what the formula would give me, I can see that what it would be is A11, and then instead of B22, it would just be another A, it would be A22. And then you would have A12, A21, and then you would have A21, A12, and then you would have A22, and then the B11 turns into A11 again. And the axiom says that that has got to be greater than or equal to 0. Excuse me, greater than or equal to 0. So I would like to check whether that seems like it would always be true for this formula. Does anybody see anything I can do with this formula? Not just some random values. Is it possible to clean it up a little bit? I simply took the formula that they gave us and I replaced all the B's with the same A's because it's the same matrix twice. That's all I did, right? So that's why I don't have any B's here. It's just all A's because I'm working on the first axiom, which says I'm going to use the same matrix 2 times, right? Both places. Can I clean that formula up at all? Go ahead, Homan. Yeah, how?
By like 2 times A.
There's 2 of the A11, A22 terms, right? Okay, so good. So let's just do that. A2 times A11, A22. And then the middle 2 terms are actually also identical. So there's 2 of those as well. Let's just factor the 2 out. So I'll just use some parentheses here and factor that out. So this is just a simplified version of it. Now, my question is, do you think that this has to be always positive? Or would it be possible to make a matrix where that would come out negative? Adrian? If we made a bunch of negative numbers? I think if all of the numbers are negative, then you'd have a negative times a negative, which would be positive, and a negative times a negative, which would be positive. But if some of my numbers are negative, I bet we could make a counterexample. I bet that this is not always greater than or equal to 0. Let's just put the word always next to that. It is not always greater than 0. That's the axiom. The axiom says it has to be for all vectors. The inner product of the vector with itself has to be greater than or equal to 0. So what do you suppose I'm going to want to do here to really be convincing about it? What's that?
Use some values to prove.
Make an example. Yes, get some specific numbers in here. Let's actually try to make a matrix, guys. Let's try to make a matrix here. If we take 4 numbers, and I just want to make sure that this thing here comes out negative. Okay, so how about I make A11 positive, but so I would use a 1. You can make your own numbers up if you want. It really doesn't matter. Let's just put a 1 and I'll make a -8 there. And then in the other 2 slots, actually it doesn't even matter, just make zeros. Let's do something like that, right? So if I do that, then for that matrix, the inner product of A with itself, according to this formula, it would be 2 times 1 times -8. And then the other part of it is just 0. And that is less than 0. And so the inner product of that is -16. That is less than 0. And so axiom 1 fails. And so is it a valid inner product? No. Right, so it's not a valid inner product because that axiom actually fails to work. Okay, that makes sense to everyone? Yeah, okay, so I always recommend starting with the first axiom. A lot of times that's the one that doesn't tend to work out, so it's good to check that one out before you do anything else. There was, from this assignment, there was just a couple of others. Oh, yeah, let me go to this next board and I'm gonna do one more problem here on this section, then we're gonna move on to some new stuff. Number 12. Number 12, they actually give you a couple of 2x2 matrices. So they give you A, which is 3, 2, -2, and 4. And then they give you B, which is the matrix 1, 1, -2, and 1. So we make these 2x2 matrices here. And they ask you to find the angle between A and B. Find the angle. So this is the idea of doing a little bit of geometry in this inner product space. Find the angle. Now, actually, the way the question is stated right now, I've been kind of cheating a little bit because why is this problem impossible to solve so far, the way I've set it up?
We haven't been given the.
We have not been given an inner product. Exactly my point. Yes, exactly. You have to know what formula are you supposed to use. We do have the formula for theta. It's the arc cosine of the inner product of A and B divided by the norm of A times the norm of B. But yeah, guys, we can't evaluate any of these things if we don't have the formula. So that formula has to be given to you. Otherwise, whoever is asking the question hasn't done their job, right? So I have to give you the formula. And the formula that we're going to use, guys, is we are going to use, I'll put it over here. We're going to use the inner product formula for the matrices A and B of A11, B11 plus A12, B12 plus A21, B21 plus A22, B22. We're going to actually use that formula to do this problem. Okay. Now, by the way, this formula looks very similar to the one that we were just looking at on that last problem, but it's not quite the same. Do you notice the subscripting? Here we had the subscripts kind of not the same between the A's and the B's. So the A11 was with B22. Well, here, be very careful. This is a little different. A11, B11, and A12, B12. By the way, this just looks like a regular dot product. And so, actually, this is another one of the homework problems, is to verify that this is a valid inner product. There is a problem in there, and that's checking all 4 axioms. But the point is that this is basically going to be working the same way as a regular dot product does. So what I'm trying to tell you guys is I'm not gonna spend the time to write out the verification of this. We're just gonna take it as a given that this is a valid inner product that we can use. All right. So we're just taking that formula, but the point is we have to be given that formula. If we don't know this formula, then we're not gonna know how to do the calculations inside of this notation for theta. Okay, so with that in mind, guys, let's solve this one out. Let's give it a go. Let's figure out the inner product of, I just want to calculate for this pair of matrices, what is their inner product? I'm using that formula right there. Okay, so the inner product is literally like a dot product. 3 times 1 plus 2 times 1 plus -2 times -2 plus 4 times 1. So let's write that down. 3 times 1 plus 2 times 1 plus -2 times -2 plus 4 times 1. So I'm literally just grabbing the numbers out of A and B, I'm putting them into the right places, and I'm gonna calculate this. This is 3 plus 2 plus 4 plus 4. That comes out to 13, I think. Okay, so that's gonna end up in the numerator of my arc cosine function. The denominator, though, is still to be determined. We have to find the norm of A and the norm of B separately. Maybe I'll go ahead and kind of work these one right on top of the other. The norm of A, as we know, guys, it's the square root of the inner product of A with itself. That's the definition of the norm. And so this will be the square root of the dot product of A with itself. That would be 3 times 3 plus 2 times 2 plus -2 times -2 plus 4 times 4. So square root of 3 squared plus 2 squared plus -2 squared plus 4 squared. Just like that. And what is that going to come out to? 25 plus 8, I think, 33. Square root of 33. Hope I have that right. Check me on that. Square root of 33, I believe, is correct. Okay. And similarly for the norm of B, the inner product of B with itself, well, that's the square root of 1 squared plus 1 squared plus -2 squared plus 1 squared. So you're just squaring up the individual entries of the matrix and adding them up. So that is the square root of 7, I think. 1 plus 1 plus 4 plus 1 should be 7. And we've got now everything we need to write down this angle. So theta will be the arc cosine of, let's see, it was 13 for the inner product of A and B. And then in the denominator, the norm of A was radical 33. The norm of B was radical 7, just like so. There's your answer. And of course, without a calculator, I would just have you leave it like this. No need to worry about it unless you have a calculator, then you can get a number and just see if it makes sense. So we have found the angle between two matrices. Even though we can't draw any pictures of it, the geometry has been infused into this vector space in this example. Yeah, pretty nice, pretty nice, pretty nice. Okay. Yeah, I did almost all the problems from that assignment. There's a couple of them right at the beginning that are really easy. I think I just won't do those. But we did almost everything else. How do you feel about that? First of all, what is your opinion? Like, would you have preferred to not watch the video and have me do it here and then do the homework? Or did you kind of like watching the video and then doing the problems here? I'm just curious.
This was cool.
This worked okay?
Yes.
Well, now you don't have anything else to turn in on this section. That's at least one nice thing. So, okay, I'm just wondering, you know. I'm planning to do this for another 40 years, you know, so I gotta learn what's the best way to explain this stuff. The beautiful thing about math is it never changes. So I don't have to worry about, oh, well, in 40 years, I'm gonna have to like change the material or something. But a lot of other fields, they have to constantly update their notes and stuff. I mean, I'm using the same notes I wrote 15 years ago right here. So that makes it really, really nice. Okay, let's spend the last part of our class. We got about 15 minutes or so. I want to hit section 5.2 real quick. At least get started on it. That way you can start on Friday's homework pretty easily. This is going to be about orthogonal vectors.
Oh, shit.
We'll just talk about this a little bit here today. And I'm just gonna jump right in with the definition of orthogonal vectors. So the question I have for you is, do you know what orthogonal means? Have you seen that word or used that word?
Perpendicular?
Perpendicular, yeah, okay, great. It's just another kind of synonym for perpendicular. But we have a definition here that's a little more math-based. So non-zero vectors, V and W, are orthogonal if. Okay, so guys, if you're telling me that they need to be perpendicular, what is the angle between two vectors that are perpendicular?
No, E,
90 degrees. And what is the cosine of 90 degrees?
0.
Zero. Zero, exactly. So for this to be a 90-degree angle, so cosine of theta, if we take that, we know that the cosine of 90 is 0. And so in order for this to be 0, right, the numerator has to be 0. How are you going to get a 0 out of this fraction? Well, if the numerator is 0. So my definition is simply that the inner product of the vectors should be 0. The dot product is kind of the way you want to think about that. Right? So if the inner product of A and B had come out to be 0 here, then it would have been the arc cosine of 0, and we would have said it's 90 degrees, which means that they would have been perpendicular or orthogonal as we're describing here. So that's just a pretty easy definition. And then to go along with that, one more definition that's just as easy, which is that an entire set, I'll call it S, consisting of, let's say, V1 and V2 and dot, dot, dot up to Vn, a set of vectors is an orthogonal set if the inner product of any two of these, any Vi with any Vj, so if we take the inner product of any Vi with any Vj, it is equal to 0 whenever I is different from j. So I is not equal to j. So for any two different vectors in my set, they are mutually orthogonal to each other, right? So that's just an entire set worth of vectors being an orthogonal set. Pretty easy. And then another definition, sorry, we have a lot of terminology here. If in addition, the norm of each one of these VIs, each of the vectors VI, if each of them has a length or a magnitude or a norm of 1, then we say S is an orthonormal set. So an orthonormal set has to be, well, first and foremost, it has to be orthogonal. Notice I said I have the words in addition. So you still have to have orthogonal vectors, but if in addition to that, they all have a length of 1. By the way, what is a vector called if it has a norm of 1? Unit vector, right? So if they are all unit vectors, then you have actually an orthonormal set. Okay, so let's just get an example up here to kind of get the idea of this. Let's take the vector space to be R4 for this first example. So these are just vectors with 4 slots in them. And then I'm going to give you a set S here. And S is going to have, the first vector is going to be 3, 1, 5, 2. And the second vector is going to be 0, 6, -2, 2. And the third vector is going to be -2, 3, 3, -6. So I'm going to give you those 3 vectors. And I'm going to ask, is S an orthogonal? And I'll put / orthonormal, because we'll just do both of these questions. Set. Question is just, is that an orthogonal or an orthonormal set? Let's just see what we think. Now, technically, you would have the same beef with me here that I brought up earlier, which is that I did not give you the inner product formula. So anytime you're talking about questions involving orthogonal and orthonormal vectors, you have to be given a formula for how to calculate those inner products. However, I did say something about this in the video, I believe, that when you're working in Rn, it is so standard to use the regular standard dot product that unless they tell you otherwise, unless there's an explicit effort to give you a different formula, you can assume here, guys, this is going to come up, right? You're going to have vectors in Rn, and you should just assume that you're using the regular dot product. Okay, you don't need to wonder, well, they didn't give me a formula. What formula should I use? In this case, it's totally legitimate to just use the regular dot product to work these things out. Okay? So maybe we can label our vectors here, V1 and V2 and V3. I've got 3 of them there. And if I want to decide if we have an orthogonal set, let's start with that one. Orthogonal set just means if I take the inner product of any pair of them, any 2 of them, we should always be getting 0. Let's just try it out. So if I do the inner product of V1 with V2, and again, I'm going to just go with regular dot product of these 2 vectors. So let's just do it in our heads, guys. 3 times 0 plus 1 times 6 plus 5 times -2 plus 2 times 2. So that's, what is that? 0 plus 6 minus 10 plus 4. That does add up to 0. So that is 0. I'll just put a little check on that. And then I have to go with the next pair, which could be the first one and the third one. So now I'm going to take V1 with V3. Let's just do the dot product again. -6 plus 3 plus 15 and minus 12. Does that come out to 0? -6 plus 3. I'm just doing the dot product of these 4 numbers with these 4 numbers. -6 plus 3 plus 15 minus 12. Is that 0?
Yeah.
It is. Okay. I know the weather's bad today. Seems like everybody's a little sluggish, but you know, we're just doing mental. Don't worry. This is like basic arithmetic. We can all, on a nice sunny day, we would all be just jumping all over these answers, right? What about the second and third one? Let's try this one. This time I take the second and third vectors. So I have 0 plus 18 minus 6 and minus 12. Does that cancel out to 0? It does. Good. So they are all 0. And so this is a yes on the orthogonal set part, right? So S, this implies S is orthogonal. It is definitely an orthogonal set, according to our definition. Now, the follow-up question would be, is it also orthonormal? So orthonormal would mean that all of the vectors are unit vectors. So in theory, we can calculate all of that also, right? So you probably could just look at it and tell me, but let's just pretend we don't know what we're looking at here, and we want to find the norm of the vectors and see what happens. So the norm of V1, right, is the square root of the inner product of V1 with itself. Just means I'm dotting this vector with itself. 3 times 3 plus 1 times 1, just write it down here. 3 squared plus 1 squared plus 5 squared plus 2 squared. And that comes out to the square root of 39, I believe. And that is not what it needs to be. It's not equal to 1. And so we're going to get a no on the orthonormal part. We're going to get a no on the orthonormal part. We don't even need to do the other vectors. If I find even one vector that's not unit vector, it cannot be an orthonormal set. So we're already able to say no here. We don't have to even look at those other vectors. Just out of curiosity though, if I wanted to see what they are, I'm gonna quickly write them down and I have a reason that I'm doing this that you'll see in a second. The norm of V2, just for curiosity, would be the square root of 0, 36, 4, and 4. So that's 44, right? So 0 squared plus 6 squared plus -2 squared plus 2 squared, and that is the square root of 44. Obviously, that's also not a unit vector. And the norm of V3, we can also do this one. Again, I'll do it really quickly just because I'm gonna show you something in a second that would be helpful to have these numbers. So -2 squared plus 3 squared plus 3 squared plus -6 squared. We do all of that underneath that radical. And what'd you get? 58, does that look right? I think that sounds right. I'll check my notes, but I'm pretty sure. Yeah, square root of 58, so 36 plus 4 plus 9 plus 9. Yeah, square root of 58. So none of these are unit vectors. So you do not have an orthonormal set. S is not orthonormal. It's orthogonal, but it's not orthonormal. So here's my question for you though. Could we do something to make it orthonormal? Homan?
I know the values by the.
Divide each vector, or actually, I hate using the word divide in this class. Let's scalar multiply by the reciprocal of the norms, right? So you can make the vector into a unit vector by scaling through by the reciprocal of their norms. So we can make S into, we can make S into an orthonormal set using scalar multiplication. So I'll show you here. Essentially, maybe I'll call it S prime now. I'm just gonna take the reciprocal of the norms. So the square root of 1/39 times the vector 3, 1, 5, 2. That would be the first vector that I would have. And then for the next one, I would have to take 1/radical 44 times the second vector, which was 0, 6, -2, and 2. And then I would have to take 1 the square root of 58 times the third vector, which was -2, 3, 3, and -6. So you can make these vectors unit vectors. I think I talked about that in my video, right? That you can take a vector and if you divide by its norm, it becomes a unit vector. It shrinks it down to a unit vector. So now you actually have an orthonormal set. Yeah. That look okay? Does that make sense? All right, well, that's a great place to stop for today. It's pretty easy concepts here, definitions. We'll do a couple more examples on Thursday of this, and then I'm going to explain the Gram-Schmidt process to you. You're going to love that. Yeah, I actually think you will like it. Anyway, we're done for today, guys. Be safe getting around today outside. It's all really, really wet. Take care of yourselves. I'll be around if anybody wants to talk about anything else that's going on with class. I'll be here. So have a good rest of your Tuesday.
Bye, YouTube. You have to say.